Okay, so in this video we're going to be going over the assumptions that you can make to simplify the Navier-Stokes equations. Alright, so the Navier-Stokes equations are partial differential equations that express the conservation of mass and momentum for a fluid. And if you solve these, you can solve for the spatial distributions of velocity and pressure. Right? And so you can see the Navier-Stokes equations at the bottom of the screen. The problem with this is that these equations are extremely complex, and actually they're literally impossible to solve. Just out of the box like that. Okay, and so in order for us to obtain useful analytical solutions, we need to simplify these equations dramatically by applying assumptions to cancel out the terms. Okay, and in fact, I always tell my students it's always a good idea to write down your assumptions whenever you're doing the problem. Right? I know it's easy to get lazy. I do that too, and a lot of these assumptions are standard. But I always tell my students, just write it down anyway, just that you know exactly kind of what you're doing when you're eliminating these terms, right? Because I think that's part of what's learning fluid mechanics is not only just doing the problems, but really understanding what you're doing and understanding all the assumptions that you're making. Okay, so let's start with the first one. So the first one is the incompressibility assumption. And so we've kind of already implicitly assumed this because we're using this form of the continuity equation. If we did not assume incompressibility, say we have some kind of compressible gas, then the conservation of mass equation would look very different. And in fact, it would have a lot of density terms. But because we assumed incompressibility, a lot of those density dependencies kind of just go away, and we're left with this formula right here for conservation of mass. And so there's nothing to eliminate, we kind of already implicitly assume that. Okay, so now let's work on the momentum equation. And so the first assumption we're going to make is 1D flow. And this is a big one because then this is saying that we only have one velocity component. And for most problems that we do, this component is going to be in the x direction. And so whenever you see the velocity components in the y and z direction, v and w, you can go ahead and eliminate those from the equation. And so we have those two terms there. Okay. And one other thing that this assumption does that you're not seeing here is that it also eliminates the other two momentum equations, right? So remember, Navier-Stokes, we have three momentum equations, one in the x, y, and z directions. But if we only have 1D flow, then we can eliminate the y and z directions outright. Okay, so the next assumption we're going to make is fully developed flow. And so what this basically is saying is that, if you look at the velocity profile and you look and see how it's changing in the flow direction being the x direction, right? We've already chosen x to be our flow direction. Fully developed flow says that the profile is not going to change in that direction. And so if you flow, if you go from one point in the flow and you flow along to another one, the velocity profile should look exactly the same. Okay, and so any derivatives with respect to x of the velocity, we can just eliminate those from the equation. Okay. Alternatively, you can obtain this exact same result by applying the previous two assumptions, or in other words, applying the 1D flow assumption to the continuity equation, because then that eliminates partial uv, partial y, partial w, partial z, and then you end up with partial ux, partial x is equal to 0, which is the exact same as fully developed flow. All right, next one's pretty simple. Next one, we're going to assume steady flow, and so any time derivatives are going to be equal to 0, and so that's just the first term right there. Okay. All right, next one we're going to assume is we're going to assume a planar flow profile, and so this tells us that we're going to assume that we have no changes in the z direction. Okay, and so traditionally, the way we usually draw problems, the z direction is usually going into the page and out of the page, right? So x is horizontal, y is vertical, and z is coming out right at you. Okay, and so we're going to assume that we have no changes in that direction. And so any derivatives with respect to z, we can just go ahead and eliminate those. And we have one such term here on the right. Okay, so those are all the standard assumptions, and so those are going to apply to most problems. The next two assumptions depend on the situation, and for these ones, you really have to look at your problem to see if it's valid. Okay, and so the next assumption is going to be no gravity force. And so you can see I've circled in blue there the gravity term. And so if your flow is purely horizontal, then gravity is not going to play a role in forcing that flow forward because it's going perpendicular to the gravity vectors. Okay, and so in those situations, you can go ahead and eliminate this chi term. But again, this really depends on your situation. And so if you have vertical flow or if you have flow that's going down a slope, then gravity is going to be relevant and you need to keep it in the equation. Okay, so check your equation. So check your problem, check your situation. If it's horizontal, you can eliminate G, but if not, you got to keep it in there. All right, so the next one is no pressure force. So this one's a little bit tricky. And so there are situations where we can eliminate the pressure force. And most of the time, those are going to be when you have a free surface in the flow. Okay. And so by free surface, what I mean is that one of the lateral surfaces of the flow is open and connected to the atmosphere. Okay, and so I found a figure online to kind of illustrate this for you. And so in this figure here, the bottom here is a wall, but this top here is unbounded. And so there's basically, you know, sunshine and clouds and birds chirping all above this flow here. Okay, and so because we have this free surface right here, it's very unlikely that this flow is going to be driven by a pressure gradient. Okay, so pressure gradients are normally indicative of internal flow, and so if you think of flow in a pipe, where the flow is surrounded on all sides by a pipe, those are usually the situations when you have pressure gradient. Okay, and so again, you know, you have to look at your problem and see if you can set the pressure equal to 0 or not. Okay, but in situations that you can go ahead and eliminate that term from the equation. Okay? And so if you apply all those assumptions, you can see we've done carnage here. So it looks like you know, my English papers back in third grade, my teacher would just murder it with the red pen. But as a result, you know, we've simplified this greatly, and so we only have a few terms left. And then from these few terms, you should be able to directly solve this differential equation to compute the velocity solution.